isn't it? And nothing but Ti minus Tg. Right or wrong? Now I can say that if I say that for Lewis number equal to 1, we know that Hg by Ky is equal to Ch, isn't it? So I replace this one, now becomes my Ch. So what will happen? I will write again, the left hand side stays the same. I'll just modify it. Right, and right hand side would be Ky bar dz. So it is Ch Ti minus T. Sorry, I should write the first term first. It is nothing but lambda 0 yi bar plus Ch Ti minus Tg. Now, if you observe carefully, that I can write down this entire component, this entire part, as nothing but H I prime minus H prime, right? Because it is Ch Ti minus To is equivalent to lambda plus lambda 0 lambda y prime, that is equivalent to Hi. And similarly, I can write also H, so that I can just take a subtraction of the reference value. I can then write this as H. So this equation is essentially the critical or the important equation here. And how you define your this height is that if you do integration on both sides. So let me write it down clearly. So what we got gs dh prime is equal to Ky a bar dz Hi minus H prime. So what I can do, I can write down this dH prime by Hi minus H, isn't it? I take an integration on both sides. Here the integration from 0 to z, and here we integrate from H1 prime to H2 prime. That's the entire height, isn't it? Is this clear to everyone? So all of you now can easily identify that if I write my z is equal to this ntg cross htg, so where htg is gs by ky a prime and ntg is this integration dh by this is from H1 to H2. So this, as you know, this NTG is the number of the gas enthalpy transfer units, and HTG is the height of the individual gas enthalpy transfer units, and this has nothing to do with the theoretical, trays in the cooling tower. If at all you are talking about a tray type column, if you are talking about a plate, this packed type column, then these are just theoretical estimates to represent or to calculate the height of the cooling tower. Now, important point is that how will you make this integration? Or how do you estimate this NTGs? That is bit of crucial here, because corresponding to the different values in between between H1 to H2. So if I go back here, corresponding to the different values of from this point to this point, what are the appropriate equilibrium values is something that you need to know to evaluate that integral, right? Because Hi prime is the equilibrium. So this is the equilibrium curve, equilibrium enthalpy values, whereas H is the enthalpy values on the operating line. And you somehow, I mean, somewhat you have the idea that for that we need to, have a construction of the tie lines. So tie lines actually help us to get the appropriate, this value of the equilibrium enthalpies corresponding to the particular enthalpy in the operating line. So something like these sort of parallel lines needs to be constructed, and then we read this is the enthalpy value at equilibrium, this is the enthalpy value on the equilibrium line. So how and what is the equation for the tie lines? So for the tie lines, what you do is that for the estimation of the tie lines, you try to make a balance between this heat transfer. So it is the same thing. It is between the so see, there are a lot of things happening. One is the evaporation. So there is transfer of the water vaporized molecules, along with there is heat transfer due to vaporization. There is also heat transfer from on the air side because the air temperature is higher than the water temperature. There is also sensible drop in the temperature in the liquid side also. Right, so if I try to write a balance, if I try to write a this in volumetric heat transfer balance on the water side of the interface to that of the heat transfer on the from the gaseous side. So what I try to mean is that ultimately this heat is balanced. What is that heat that is balanced? That the drop or the change in the liquid temperature is equivalent to the the heat of vaporization due to this vapor transport, and that is equivalent at equilibrium, right? That is equivalent to the rate of heat transfer from the gas side to the liquid side, isn't it? All three of them are in balance, is it or is it not? Right, so now think about the water side system. So since the water there is as compared to the heat transfer from the gaseous side, on the gaseous side, in the same way you can also write down the heat transfer on the liquid side also, isn't it? So in the liquid side there is loss of heat due to drop in the temperature, right? And which is basically due to the evaporation of water. And this part can be equated to the rate of heat transfer from the interface to the liquid side, because the interface temperature is higher than the bulk water temperature but lower than the bulk air temperature. So there is heat transfer from the bulk air to the interface. There is also heat transfer from the bulk water or inside the water droplet to the interface, right? And this heat transfer is equated to the drop in the temperature of the liquid water, which is also equated to the this rate of heat loss due to the vaporization, isn't it? So if I try to write down the same thing here, so sorry, so this is the LCWL. So this is the heat, the change in temperature or the drop in the sensible temperature on the water side. This is equated in the same way as the water side heat transfer, HL, like how we did it for the gaseous side. Same I can also write for the water side, because the interface temperature is higher than the water bulk temperature. So this one is TL minus TLI. Is it or is it not? Now you very well, I mean, by now you have already realized that this is equal to GSTA, change in the enthalpy of the gaseous side, right? and that this is equal to, we have just now calculated that this GSDH prime is equal to KY A bar DZ HI minus H, right? So now we are trying to equate these two. So what we have, what we get, KY A right? Or I can also write down in the reverse way and put a minus sign here. I can this to be right. I can also write like this, isn't it? So this equality can be established from here. Now instead of writing GSD H prime is equal to this KYA this thing, right? You can also write this to be in terms of Li. So what essentially this means that I have, so if you equate these two, what this gives you, that HI isn't it? So this is the equation that you get, and this is the equation for your tie lines, which connect the points on the operating line to the equilibrium enthalpy on the enthalpy temperature curve, and the slope of this is minus HL by KY. So please remember, this HL is the heat transfer coefficient on the liquid side, not on the gas side. Okay, so this HL is the liquid side heat transfer coefficient. So one more thing also, another easier approach, instead of this integration that you have, right now we have this NTG as dH by HI minus H. This range from H1 to H2, right? Now since this GSDH prime is also equal to LCWL DTL, we can write that instead of this formation, this is from where you got this, isn't it? This is from where you got this NTG. I can, instead of that, I can write LCWL DTL is equal to DZ, same thing, HI minus H, right? So what does this gives me now? This gives me DTL by HI minus H bar is equal to or I can write it on the left side itself. So this part is HTG, and here the temperature range is from TL, what should I write, inlet, so that is TL2 to TL1. No, it's just the other way around. It's from TL1 to 2. Right, so this part is the NTG. So what is the benefit of here? Here, instead of calculating this NTG with respect to the H1 to H2, you can also get it calculated on the temperature side. Okay, just a different alternative form of the NTG. It's not that this should be preferable, not that, but just to give you a different, this form of the NTG. Is this clear to everyone? Something which is not clear, guys, please let me know. So if this is all fine, we just have a this guideline of the steps of calculation, and possibly in the next class we will do a sample problem. So what are the steps? The first step is specifying the inlet and the outlet temperatures and the flow rate of the water or air, whatever these informations are available, right? So these informations are generally correlated with the requirement of the cooling water in the heat exchangers or in the other downstream processes or upstream processes, right? So that is how you specify the inlet and the outlet conditions, their temperatures, their flow, whatever information is known, right? The second step is to have the design values. This is a very important thing as a part of the designer, is to have these design values for the dry bulb and the wet bulb temperatures of the air, right? And this should be obtained based on the weather data of that geographical location where this cooling tower will be installed, right? And that this wet bulb temperature actually determines the approach, right? And this approach you have to maintain certain level of this approach, and this wet bulb temperature is the highest during the rainy season possibly, right? So whatever this value that you get of that location on the rainy season should be chosen as the wet bulb temperature, because if the cooling water can operate in the rainy season, it will also operate according to the designed specification in the other seasons where humidity is low, and accordingly the wet bulb temperature is low, so the approach will be higher, right? Higher is the approach, the more is the heat transfer, right? But lower is the approach, the size of the cooling tower also reduces. So there is a trade-off. So you should design your tower such that it can perform the designed condition, or it can give the designed performance or the rated performance at the worst condition, and the worst condition is the high humidity season. Right? After you do this, the third step is to draw the equilibrium curve, the enthalpy temperature curve, and this is nothing but the 100% saturation line that you get from the psychometric chart. Right? For 1 atmospheric pressure, this equilibrium data is always with you in the form of the psychometric chart. So this is one big advantage here, that you do not need not to draw the equilibrium curve separately. If you just take your psychometric chart, the 100% saturated line will give you the equilibrium line, and you can start working on the operating lines and from there on. Now the fourth step, after you draw or identify the equilibrium line, the fourth step is to identify the lowermost point, which is the inlet of the air and the outlet of the water. Most likely these informations will be known to you, because the outlet of the water is the desired temperature that you want from your cooling tower design. Right, so that information will be known to you, and also the inlet of the air, which is surrounding air, which will be coming, will also be known to you. And there accordingly their characteristics, etc., their enthalpy values and all based on their humidity, you can locate that point, right? You can locate that point. So effectively what I am talking about is something like this. So let us say you have this sort of the equilibrium curve, which is nothing but the 100% saturated line, 100% this this saturated enthalpy line there that you have, this enthalpy versus temperature curve. Okay, and over that I am just talking that you fix this point 1 or the bottommost point of your cooling tower, right? And what is the next step? The next step is to draw a tangent from here. Try to draw a tangent from here, and you try to get the slope of that tangent. Right? Either you can draw a tangent, or if you have the knowledge of the inlet quantity of the water, right? Most likely that will be known to you. What will be the inlet temperature? So the temperature difference that you want to make in your cooling tower is something that is pre-decided. So based on the this inlet water temperature, which is from the top, another point, and then you try to draw a straight line which intersects or touches this equilibrium curve at the inlet cooling water point. Very similar to the absorption column design on this part, right? And the slope of this line, from the slope, whatever this value of the slope that you get, the slope is what? The slope is LCWL by GS, right? This is the slope. So either the liquid flow rate or the gas flow rate will be provided to you. It is most likely the liquid flow rate that will be mentioned to you, because that defines the circulating water rate and the cooling tower capacities also, right? So the liquid water rate is generally provided, and that is decided on the this process engineering, right? So you need to find out from this slope what is the gaseous velocity for the minimum condition. At the minimum condition, the tower height is infinite. Okay, because you will be the NTG, this at the minimum condition, whatever this you get, there will be a point where, the exit conditions of the air water would be equilibrium, and to achieve that condition you need an infinity tower, right? So you generally do not operate that. You say that we want to operate at a condition higher than the minimum configuration. Let us say whatever the gas flow rate that you get from the minimum condition, we say that the actual gas flow rate is double of that, is to be provided, something like that, or more, or at least 50% higher than the minimum value that is needed, right? So now that fix your gas flow rate. Once your gas flow rate is fixed, you have to decide that whether you are going for what kind of airflow pattern or configuration you want to achieve, whether it's a natural draft, or if it's a mechanical draft, then whether can you achieve this in induced draft, or do you need this forced draft condition. So these are the conditions that needs to be determined based on the gas flow rate, right? Please note that higher gas flow rates will need more of these induced or forced mechanism. But if you are okay to not invest more on the operating cost due to the energy of the fan, you have to, then the gas flow rates would be low, and in that case you will be more like you are making transition towards the natural draft. So the column tower height would be much larger, right? So natural draft towers operates at values of the this gas flow rate very close to the minimum value flow rate, right? So it will require less amount of flow rate, and naturally the tower height will be low to achieve the equilibrium value, whatever this height you need. So that's the reason you will find these towers to be very high. The higher gas flow rate you have, the tower height will reduce, right? But that will cost you energy in terms of operation, right? So based on that, you decide whether you want to, I mean, what is the gas flow rate that you want to decide, whether you want to go for induced draft, forced draft, and what's the amount of energy that you wish to spend or your client wish to spend on this. Accordingly, the size will come up. The larger is the site, there is also cost associated to its construction, but energy cost will be low. The lower is the, so there is an optimization, right? How much on the cost perspective, but what is the operating cost and what is the capital cost? Capital cost for low airflow systems is high, but capital cost for high airflow systems are low, but the operating cost there is high. So there is an optimization in that part on the design of the cooling tower. That's how you are going to select the, I mean, based on these, policy decisions, I would say, you are going to select your gas flow rate. And once the gas flow rate is selected, then you draw the operating line, right? Now your this thing is already decided that what is going to be the your operating line, where the slope is decided. You also know the final point because the outlet temperature of the, sorry, the inlet temperature of the water is also decided, right? So accordingly, you fix your this thing, your operating line. Okay, so you draw your operating line. Once the operating line is drawn, the next step, is to draw as many tie lines as possible, right? And at each of these tie line positions, you mark the equilibrium values, right? And correspondingly, you mark the enthalpy values and the operating line. So based on this information, you can calculate this NTG. So this is from the equilibrium curve you have to get, and this is something you have to get from the operating curve. So this equilibrium curve things has to be dependent on the tie lines, and you construct as many tie lines as possible. So these are discrete points, right? In between the interval of H1 to H2, these are discrete points, and the corresponding information on the equilibrium curve is given in HI prime, right? So you make a table of your H with respect to 1 by HI minus H. This table you make, right? So you list down the corresponding H values, right? And these H values would be the values on the operating line. Okay. So you write down these values and correspondingly you fill this table. So once you get some discrete points, you know how to do numerical integration by Simpson's 1/3 rule or trapezoidal rule or whatever, right? And then you get your NTG. And HTG is something you already know. HTG is something that you already know. So HTG is nothing but this sorry. Sorry, KYA by GS. Right, this would be your HTG. So you make the product of two, and then you get your. Sorry. I am writing the reverse. Right, so higher is the gas flow rate, higher is the HTG value. Right. So in this way, you get your height of the cooling tower. So anyone has any questions on this? If not, then in the next week we will do a worked out example from a textbook. In the class, I request everyone to have your psychometric chart available with you, so that it is much easier to work out the problem. Any questions, guys? If not, then we stop here for today. And again, we will meet you on Tuesday. Is that good?